So welcome all back. Just to remind you of where we are in our quest to understand parallel computing, we have finished line 5 up there. We did dense linear algebra, a couple of lectures on that. And we are now on the last lecture for the sparse linear algebra. And next time we will start n-body. But just to make sure we understand why I'm telling you so much about sparse matrices, but maybe before I begin with that, we have a few announcements related to homework and other matters.
I have uploaded the homework zeros. What we've done is we've made a spreadsheet where we just tried to guess what your title was if you didn't tell us and summarize it briefly. These homework zeros were really for you guys to help find potential partners for projects. So if you go to the resources page, the homework resources page, after homework 0, it says results. Click on that and it'll take you to a Google Doc. Please email the CS267 SP12 Gmail account if there are dead links there, because I did I copied a lot of that by hand. Yeah, so that's a good way. There are no email addresses there. I think you can actually see people's email addresses through Piazza for the class. And I think that was it, right?
And homework?
Oh, which homework?
Maybe you just want to make that announcement because it's not
it's
visible to everybody on
okay,
the
yes, homework 2 is now due March 15th, parts 1 and 2.
Due to popular request. Yes, many popular.
Sorry if anyone pulled an all-nighter.
Okay, very good. So someone last time asked, why are you telling me so much about sparse matrix vector multiply? Well, it is a major component of that sparse motif that I was just showing you. And we're going to build on it and do some other things that are much more complicated. But let me just say a little bit more about what does go into that sparse motif, that sparse dwarf. There are two things. There's direct solvers and there's iterative solvers. In the direct solver case, that means either ax equal b or least squares. And we haven't spoken about that very much, but I want to give you a pointer there to a web page which has a constantly updated report, which has a list of all the best tools and available software. And what you do is you say, I want to solve either ax equal b or a least squares problem. I know whether my matrix has certain properties like symmetry. And I know whether I want to run on a sequential machine, a multi-core machine, or a distributed memory machine. And it has a list of all the best available software. So you can go look at that. But what we're talking about here are iterative solvers. And again, that covers a much broader range of problems you want to solve. And these are basically used when you can't afford any of these direct ones. When your matrix is so expensive, the only thing you can afford to do with it is a sparse matrix vector multiply. And the general class of these algorithms are called Krylov subspace methods. And at the end of this lecture, I will come back to what they look like, because we have to actually change those significantly to make them run in parallel. And again, there's lots of good tools available and online guidelines to help you pick the right algorithm, because it's even more complicated now depending on which of these 4 basic problems you want to solve: linear systems, eigenvalue problems, depending on the properties of your matrix, depending on what you want your answer to look like. Do you want a lot of the eigenvalues, the eigenvectors, or whatever? There are these online books which give you decision trees to help you choose the right algorithm. And in the last lecture, I told you about multi-level methods. Those come up too. We'll have a separate lecture on that later. So here, just to show you, is what an example of what one of those decision trees looks like to help you choose the right algorithm. And I'm only going to talk about one of these algorithms at the leaf of the tree at the end. So you might ask, the first question is your matrix symmetric? That gives you a different choice of algorithm. And if it happens to be symmetric, then you come over here and you ask the next question, is it a definite, positive definite matrix? Are all the eigenvalues positive? That comes up very commonly. And if that happens to be true, you come down here and you say, well, do I happen to know roughly what the largest and smallest eigenvalues are? That's a pretty rare situation. So usually the answer is no. And in that case, you try an algorithm called conjugate gradient, which is very well known. And depending on what other answers you may give to these questions, you come up with other algorithms like GMRes, QMR, and so forth. And we'll say a little bit more about what are the general ideas to make these things run fast and minimize communication. But we'll do that later. Okay, I have one more sequential algorithm optimization I want to tell you about, because it illustrates the fact that if you really try to make sparse matrix vector multiply go faster, you have to change the higher level algorithm that calls your optimization. So it affects the mathematics higher up. And let me just show you what this is. So this is an example of a matrix that we got from people who were designing particle accelerators. It's symmetric, so we want to take advantage of that optimization. We want to do register blocking. That was one of the main things that worked. But it turns out this matrix did not have very many dense blocks in it. On the other hand, if we were reordered the rows and columns, so it's still the same matrix, we've reordered the rows and columns, we could create very large dense blocks and make it go a lot faster. And so there are two kind of graph theoretic algorithms that we use to make this run faster. The first one is we reorder the rows and the columns to push all the non-zeros as near the diagonal as possible. If you push the non-zeros close together, chances are you'll find bigger blocks. What's the algorithm for doing that? Historically, it has this long name, but it's basically breadth first search. You run breadth first search on the graph and use the ordering that comes out of breadth first search. And I'll show you a picture in a second. That does an excellent job, but it's not quite perfect. There's another optimization you can do. What you want to do is reorder the columns so that adjacent columns have a lot of non-zeros in common, a lot of non-zeros in the same rows. So what you do is you make a graph. There's one vertex for every column in your matrix, and you say that these two columns belong together if they have a lot of common non-zeros in the same rows. So you put a weight between those two vertices that says it would be good if these guys were side by side. That turns into something called the traveling salesman problem, which is a well-known optimization problem too. And by the time you did all that, you got big speedups. So let me just show you the pictures. So here was the original matrix, just a spy plot. So everything is scattered all over the place. And so as I said, the first thing we do is we reorder the rows and columns to try to push everything close to the diagonal. So I run breadth first search in that graph, and this is what it becomes. You can see I've done a pretty significant job of pushing all the non-zeros close to the diagonal, and it's nothing other than breadth first search. So let me zoom in and see how good a job I did. So I'm just going to zoom into the leading 100 by 100 submatrix. This is kind of typical, so that's what it looks like. And you can see that each blue dot is a non-zero, and there are not very many that are close together. So what happens after I do breadth first search? Here's a before and after picture. So the green dots, the green non-zeros, they didn't move. They were the same before and after. But the red ones are before, and the blue ones are after. So all the red dots got moved, the red non-zeros got moved into the blue spaces. And you can see there's a lot more clustering of them, and there's a lot more opportunity for blocking. And so one more optimization, as I said. What about traveling salesman? Let me just toggle between the pictures. So here's traveling salesman. It was a sort of a small change at the end. Oops, sorry. But if I go between these two, you can see that, for example, these two little guys, they now go together, and a lot of those little changes went everywhere. So anyway, what is the bottom line? The speedups range from, well, it depends on the different computer you were running on. Factors of 2, 3, 1.5, 2.1. And so these were the speedups that you got. And I've sort of broken it down here depending on which optimization you used. There was just symmetry and just blocking. That didn't do so well because there weren't very many large dense blocks in here. And there's if you throw in traveling salesman, and there's if you throw in everything. Symmetry and traveling salesman and, well, reordering and blocking. So you had to do all of them to get these speedups. And so that gives me a much faster sparse matrix vector multiply, but I've changed the matrix, right? I've reordered the rows and columns. And so x and y, if I'm doing ax equals y, I have to change x and y too. So that's going to change your algorithm. And so the question is, how does that affect the higher level algorithm? And so you have to think, sort of go up the stack one and make some changes there too. And sometimes you can save a lot more at the next level. So let me just call A the original matrix, A super P my permuted one, so I've reordered the rows and columns. And so the naive thing to do is simply, whenever your original algorithm needs to multiply by A, you're going to permute the vector x, multiply it by AP, and then permute the output to sort of undo the permutations. And so that means every time you do a sparse matrix vector multiply, you got 2 more permutations. That's a lot more expensive. So let's get rid of that. So let's solve AX equal B and ask ourselves, how do we do it? So let me notice that I can write this permuted matrix as a product of a permutation, the original matrix, and the permutation, well, transpose on one side, okay? So that's what permuting means. I'm just multiplying by a permutation. I never actually write down this permutation. It's just a list of indices. So then what I do is I don't solve the original problem. I solve my permuted matrix times some new unknown equals a permuted right-hand side. And so I solve this using one of my algorithms, and all I need to do is sparse matrix vector multiply with my permuted matrix. I never need to do any permutations except this original one. And then when I get the answer out, I do one more permutation. So the only time I have to permute my vectors is once at the beginning, I permute B, and once at the end, I permute X. instead of doing it for every matrix vector multiply. So that makes it significantly cheaper. And it's even better for the eigenvalue problem, because let's compare A and AP. A and AP are similar. They have the same eigenvalues exactly. The permutations are irrelevant. I can find the eigenvalues of AP, and they're still the right ones. And if I want the eigenvectors, there's also, I can just get myself down to one permutation at the end. So this is the simplest case where we can save something by looking at the next level. But when I do more sophisticated optimizations later, we're going to have more complicated transformations to higher level algorithms. Okay, so that's the end of the sequential optimizations. And the next one is how do I do tuning in parallel. And so what I want to do is show you some results on 4 different platforms, 4 different multi-core platforms. So an AMD Opteron, an Intel Xeon, a Sun Victoria Falls, and a cell blade. And so what I put these pictures in here for is to sort of just distinguish the architecture so we can get some insight as to which optimizations make sense. And so the color coding here is all the orange stuff are the cores. Those are what run in parallel. The blue things are caches, and so this little thing means that this cache is shared by these 2 guys. So these 2 guys can access this one equally fast. And then there is green is the DRAM. Okay, and so in this case, there's one big shared DRAM for everybody. So that's all equally quickly accessible from everybody. But here, they're separate DRAMs. And so these guys can get to this DRAM faster, but if this core wants to access that DRAM, it's going to be slower. Okay, so this is all going to affect how we do our optimizations. So let me just sort of distinguish the high-level issues in the architecture. So everything here that's not whited out is a traditional core-based memory hierarchy. So you do a load, you do a store, the hardware figures it out, it behaves the normal way. And on this IBM Cell Blade, there are 2 processors which behave that way. They're sort of the control processors. But on that machine, there's a different memory hierarchy for the 16 cores that do most of the work. Here you actually have to do explicit load and stores, data movement instructions. No, there is no cache. You have to call a subroutine which moves data from main memory into these guys' memories and to put it back. So that's a different memory architecture. So here's another distinction. Most of these processors have hardware cores. Each one runs 1 thread at a time, and you have to control how many threads you want to run. But not on the Sun Victoria Falls. It has something called chip multithreading. So it automatically generates lots and lots of hardware threads that run on here, and if one is waiting for the memory to do something, it will automatically switch and run another one. And so this is a different threading model where there's lots of threads created automatically and managed by the hardware. So there's lots more potential parallelism here in the sense that you have to keep it busy, you have to create a lot more work to hide the memory latency. So overall, how many threads are there in these machines? So for this one and this one, there are 8 cores, there are 8 threads. That's how many you have to create and run at the same time. Here, because the hardware is managing it, there are 128 threads that you have to create to keep everything busy all the time. So that's a lot more. And then here, for the 16 SPEs, those are the little parallel guys that just are sort of SIMD processors. There are 16 of those. So you want to have 16 threads to keep those busy. Okay? So the other issue in this optimization is that some of these platforms have non-uniform memory access, as I said before. So here, this DRAM and this DRAM are directly connected to separate processors. So if this core wants to go get data there, it's much faster than if he has to go over that bus and then go get data out of that core. That's true for these 3, but for the Intel Xeon processors, it's uniform memory access. So this is all of these optimizations are going to be taken into account. And so all of these results are from an CS267 paper, and you can look up the details there. So let me tell you what the test matrices are, and then what the optimizations are, and then I'll show you how important each one was. So there were 14 matrices, all chosen to be much bigger than the caches of any of these processors. And so you always choose a dense matrix just to see how well you do there. There are a whole bunch of nice, well-structured finite element matrices that we've seen many pictures of. Then there were some other ones which were mixtures of different things, hodgepodges of various kinds. And then there was one really long, skinny linear programming matrix that represented constraints in some problem. And so this is harder simply because it's, it's so far from square. And that's going to make a difference in how we have to do caching to store the x and the y vector. So the basic parallelism is going to be really simple. For the naive, the base case is we're just going to break the matrix up into row blocks, and each thread will do one row block. We've seen that before. And how do we decide how big these are? We'll just do load balancing by counting non-zeros. So if I have 4 cores, each one will get a quarter of the non-zeros. So these aren't necessarily equal number of rows, they're equal number of non-zeros. So let's see how well that does. So our baseline is I'm going to create 8 or 16 or however many threads and run it and see what happens. So here are the speedups, just to see what the naive parallelization does. And so there's the x-axis is all my 14 different test matrices, and there's the median. And the vertical axis is gigaflops per second, so up is good. And the orange, purple, whatever it is the naive code, so sequential. And then the blue bar on top of it is how much faster it goes when you parallelize it in the straightforward way I just described. So this processor had, 8 cores? Do I get 8-fold parallelism? No, it's pretty far away from 8-fold speedup. So obviously there's a lot more I can do. This one also had a potential of 8-fold, and I get like a factor of 2. This had 128, but take my word for it, we're pretty far from 128 times faster. And here, this is a little artificial because remember the cell blade had 2 processors called PPEs, which were like full-blown, processors, and then it had 16 SPEs, which were the ones that you had to run in parallel, which had a simpler instruction set. This is so far only using the 2 PPEs, not all the 16 SPEs, because you can't program them the same way. These are the only ones that are programmable in the usual way. So anyway, the scalability isn't great. Let's add the other optimizations and see what they do. So what are the other optimizations? So the first one is worrying about NUMA, non-uniform memory access. So what I need to do to be careful is when I say this submatrix, block of rows, is going to be done by that core, I have to make sure that submatrix is stored in the memory that's closest to that core. And so there's special instructions that you use to pin submatrices to cores to make sure that it's not far away in a distant part of the memory. And so that optimization is there. The next one is prefetching. So there's special instructions in these machines to say, please get the entries of the matrix or the indices or the vector entries ahead of time. And the instructions will let you say, please do it 2 ahead, 4 ahead, 8 ahead. There's a parameter in them. And the optimizations did exhaustive search on all the possible prefetch distances to see what the fastest thing was. So the next optimization is a generalization of what we talked about in the sequential case. We did register blocking, call that compression, right? Where it's making the matrix data structure smaller. But there are other ways you can do that too. If your submatrix is small enough, you don't need to use 64-bit integers to store the submatrices. You can use 32. Sometimes you can only use 16. And you may use a different integer size for every subblock depending on its size. And you may not even use BCSR, because remember, when you use this data format, you have row pointers. So you need a pointer to the beginning of each row. And if your submatrix is really, really sparse, you may have a lot of 0 rows. And in that case, you're wasting a lot of space with pointers to nothing. In that case, there's a different format which takes advantage of the fact that you may have 0 rows and saves space. And so that is done. And then there's cache blocking. So what is that? Instead of just breaking up your matrix into one-dimensional blocks, so rows, 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 you break it up into 2-dimensional blocks. So each matrix may get a subrectangle. Now, why would you want to do that? Well, that's because if you give a processor an entire block of rows, it could potentially need the whole x vector in order to multiply by it. Maybe the whole x vector doesn't fit in cache. So if you give it fewer columns to work on, a smaller block, it may only need a subset of x, and then you avoid cache misses on the x vector. So that's an optimization too. So all of that is in there. So let's just make a plot and see what the benefits are. So here, it's all color-coded. It's the same thing as before. There's 4 plots for the 4 different processors. There's 14 columns for the 14 different matrices, plus the median speedups at the end. And then it's color-coded, and up is good, gigaflops. And it's color-coded by all but one of the optimizations I told you about. So the naive one is the purple at the bottom. Then comes naive parallelism. Then comes a NUMA optimization. and then comes doing prefetching, and then comes doing the compression, blocking and all that sort of stuff on top of the yellow block. And so you can see that depending on the problem, each of these optimizations was more or less important. It depends totally on the sparsity structure, so the system tries them all. And this, of course, was done largely by hand. Now there's a system I'll tell you about that does it automatically for you. But this is the level of complexity that you have to worry about to do it. Anyway, what's the lesson? Of course, surprisingly, the dense matrix wasn't always the fastest. So you would think so, but it's the first column, and it's often the fastest, but not always perfectly the fastest. Yes, question?
Does it make sense to have NUM optimization for Xeon?
Which optimization?
NUM optimization.
No. So for NUMA, there was no optimization. So I think that you will not find this colored bar appearing here. Because you're absolutely right. It's not a NUMA processor. So NUMA was only done for these other ones. Right. So if you know your processor has that property, you don't worry about it. Any other questions? Okay. So there was one optimization here I left out. I'll put it in the next slide, which is cache blocking. And I also changed the vertical scale so that I can finally put in everything about the sun blade. So now I put in cache blocking. That's the one last little, I guess, orange color at the top. And that hardly ever made a difference. The one matrix for which it made the biggest difference was the linear programming matrix. And that was an incredibly short, fat matrix. So if you want to keep the entire X vector in cache, it totally overflows cache because there's so many columns compared to the number of rows. And so it made much more sense to break up this linear programming matrix into short blocks. So you only needed a subset of X, and that's why the payoff was the largest for that particular one. And in addition to cache blocking, it says cache, local store, and TLB. And so finally, let me put in the totally hand-coded assembly language version of what ran on the Sun blade because it had a different instruction set architecture and everything for those SSEs, and that's the speed up you got there by the time everything was done by hand. So that machine is no longer the most important one. I'm not sure it's so available anymore, but these others, and their descendants are. And so the question is, how do we do auto-tuning for this? Because these are the speed ups that were gotten overall, and we would like to get this automatically, of course. So the question is, all of this was a result which was done carefully by hand to understand which optimizations were important. And what we'd really like is to have this all automated. And that's the next topic. So a system called Pyaskey, which is about to be released, and for which there are lots of class projects possible in order to enhance its capabilities, in order to automate all of these auto-tuning activities. But are there any questions about the optimizations themselves before I talk about the system that tries to make them easy to use? Okay. So I think I showed a picture of Pyaskey, the original system last time. Its icon was one of these pictures, so Pyaskey naturally consists of many, many of them running in parallel. And so this is the parallel optimized sparse kernel interface. And so right now, its current status, about to be released status, is it will optimize sparse matrix vector multiply, either AX or A transpose X, because many applications need both. And it's going to hide the complexity of all of that tuning that I was telling you about. Now there's a sequential version that's been around for a while on which it's built called plain old Pyaskey. And in addition to doing AX and A transpose X, it did a bunch of other stuff. That's all work to be done. Think class project. So A transpose times A, I think I may have mentioned. If this is what you want to optimize, you only have to read A once from memory in order to do 2 matrix vector multiplies. So you get speedups of 2 by taking advantage of that. Solving sparse triangular systems and many other things. And so anyway, let me go on and tell you about what's in Pyaskey. So, as I said, it's going to do AX and A transpose X. It has the register blocking. It breaks up things into threads. It does the SIMD optimizations, so it will search through different ways of generating that kind of code. It'll do software prefetching, pipelining and loop unrolling, and the NUMA awareness stuff. So, and in order to make it easy for the community of people who have special processors or special matrices, you can plug in your own optimization. So it has a nice friendly interface which will let you insert your own optimizations that other people can use. And the stuff I told you about reordering, not done yet, but the interfaces are general enough that other people can put them in as necessary. So the question is, how do we organize all that complexity? This is much harder than tuning gem, tuning matrix multiply, which you can kind of do once offline, put it in the library, and you're done. This one, remember, you can do some stuff offline, but you got to make a quick decision when the user finally hands you his or her matrix online. So here's kind of how the overall software architecture is broken down for tuning. So there's an offline or install time work that's done, and then there's stuff that's done at runtime, where you can't afford to spend very long. So what happens offline? So just so you know, the green ovals are the actions taken by the library, and these other things that look like databases are databases. So there's things that are stored by the library so they can be referred to quickly at runtime. So when you install it, there's a target architecture. You're going to take a benchmark for some sample matrix, say a dense matrix. You're going to generate a lot of code variants. I should say the Pyaskey is going to generate a lot of code variants for different block sizes, R by C, from 1 to 12. It's going to try different prefetching distances. And it's going to try different SIMD implementations, because you spell SSE instructions differently on different platforms. So it's going to automatically generate all those code variants. So for example, if you're doing a 4x4 block, it may completely unroll the code and insert SSE instructions. It times them all and builds a database of benchmarks. So for each block size, for each R and C, it says which were the best values of the prefetch distance and which was the SIMD implementation, and it stores that. So you can just grab it, the precompiled code that you can just grab at runtime. So what happens at runtime when the user supplies the matrix? So the user is going to supply a matrix. I'll show you what the code looks like. It's pretty simple. And the user can also give hints, because the user knows more about the matrix. And so the first thing that happens is the matrix gets partitioned so that each thread will have some work to do. And so there are going to be a whole bunch of different submatrices, 8 submatrices if you have 8 threads. For each submatrix, what the system is going to do is going to build a little performance model. It's going to say, well, what does this sparse matrix look like? What are the sizes of the dense blocks? It's going to, remember last time I talked about estimating the fill. If I build my matrix and break it up into R by C blocks, how many new 0 entries will I have to store explicitly? So it'll build a model like that. And then, looking at this database, it'll pick the best pick the best one for each submatrix. And finally, when it's done, it's going to hand the user back a nice opaque subroutine call, just one line that the user will call that will do it all fast. So it's going to hide all these details. So how does all this work? Well, what Pyaskey will do, it will monitor your program. Every time you call matrix vector multiply, it'll keep track of which matrices you multiplied, how often, what operations you did, and it'll build up kind of a profile of your program. And it may change the way it tunes depending on that profile. It will do all of that searching that I told you about, estimating the fill. But it also has a history database. Because the user's hint may be, this is the same matrix I used yesterday, right? That's not uncommon. You're going to use the same matrix over and over again. And you can skip all that searching because you already solved the problem yesterday, and you can just go grab the optimal code from the database. And finally, as I said, it just hands back the optimal code. So I think that this just says in words everything I said aloud. The only thing that is additional here is that we try to use we try to use Python to do all the code generation, and there's a lot of GNU auto tools to make all the installation easy to sort of make it as portable as possible. So the bottom line, though, is that the tuning cost is non-trivial. It can cost up to 40 matrix vector multiplies to go through this entire process and hand the user back the tuned version. So if you only want to do one sparse matrix vector multiply, don't bother. But most of the time people want to do so many that it's worth going through this whole infrastructure. So let me show you what this looks like at the user level. And I'll take some very simple sequential code and I'll change it as little as possible to use all those optimizations. So here is the simplest possible sequential code you could imagine writing. You declare your sparse matrix, so there's an array of the values of the non-zeros. This is in compressed sparse row format. And you have the array of the column indices, and you have the array of the row pointers, and you have a pointer to the x and y vector. And then you call your matrix multiply routine, excuse me, 500 times. All right, so this is the code you start with. So the question is, what do I have to do to make it run in parallel? So the first step is you're going to call an ASCII thread routine, which goes up in the system and looks up how many threads do I have and what properties do they have. So at this point, there's a threading routine. Then what you want to do is you pass your matrix data structure into an Pyaskey create matrix routine. And so what it's going to do is create its own image of the matrix in its own internal format based on what the threading mechanism is. So the threading mechanism could be pthreads, it could be OpenMP, there are different kinds of threading mechanisms, they're all supported. Then you also have to create, and that returns a pointer called atunable. That's Pyaskey's view of the matrix. All the details that I was telling you about are hidden inside this object of this tunable matrix. You also have to create a view of x and y so that Pyaskey can, if necessary, modify how x and y are stored. And so those are the first two steps, so it's a few lines of code. And then finally, you have to change your matrix multiply call into Pyaskey matrix vector multiply. And you pass in your matrix. You pass in whether the operation is multiplied by A or A transpose, and then the rest of it looks the same. The constants and the pointer to x, the pointer to y. So this is the least amount of work you could do to call Pyaskey instead. But I haven't done any tuning yet. So now we have to tell the system to please tune. And the easiest thing to do is, so now this is the same code. I've left off some of it so it all fits on one slide. I'm going to call Pyaskey tune hint. I'm going to give a hint to Pyaskey that I'm going to do it 500 times. That'll say yes, it's worth tuning. If I also know the structure of my matrix, I don't have to, but if I do, I can give that hint as well. If I know there are a lot of 8 by 8 blocks, I can give a hint which says this tunable matrix has a block size of 8 by 8. Or I could let Pyaskey figure it out itself. But if I know that, I can tell it. And then I can say please tune. So at this point, it will take your information, and if it's good information, it'll use it. Otherwise, it'll ignore it and change inside of atunable to be now this new object, including, it'll change the data structure, and it'll also change which subroutine it calls in order to do the matrix vector multiply, getting it out of the database. And then your call to the subroutine that does the matrix multiply looks the same. Okay, so that's the simplest thing you could do. Let's suppose you don't have any hints. You don't know how many times you're going to call it. You don't know what the block sizes are. So here's the most naive thing you could do. You just tune it inside the inner loop. So every time you call it, 500 times, you call tune. That seems like a bad idea. So what does tune do these 500 times? Most of the time, it just keeps track of what you're doing. It's monitoring your program. It recognizes, oh, you called matrix vector multiply, with A instead of A transpose. You did it once, then you did it twice, then you did it 3 times, and after maybe 40, it'll say, oh, I think it's worth tuning now. And at that point, it'll slow down and look through your matrix, do the sampling, and change the data structure for atunable and change the subroutine that's actually called to do the matrix vector multiply. So that is like the simplest thing you could do. Just let Pyaskey do everything. So there's a whole manual, draft of a manual, which you're welcome to look at. But that's the simplest way you could possibly use this. So here's some performance results. And this is comparing it to Pyaskey. So all of the sequential optimizations, but still just one processor. That is the blue. Then MKL, the Intel tuned library, has its own sparse matrix vector multiply inside. That's the red. And then Pyaskey's in yellow. And so you can see there's good payoffs for all these different platforms. And so that's the easiest way to call all this tuning stuff. Are there any questions about that before I go on to the next topic? So I think I've told you everything there is about SPMV, and is that all we can do? Because, of course, why am I bothering to do SPMV? As I said before, I really want to solve a system of linear equations. I really want to do image processing. I really want to find eigenvalues and eigenvectors. There's a higher level algorithm. But if all I do is look at this kernel, sparse matrix vector multiply, then my speed up is going to be pretty limited. Why is that? Because I only can do 2 floating point operations per non-zero, right? That's what matrix vector multiply looks like. And so no matter what I do, the communication costs are really going to totally dominate it eventually. And so the thing is, if I want to reduce communication further and become, hopefully, CPU bound, arithmetic bound, then I have to look up at the next level in the algorithmic stack. What am I doing with all these sparse matrix vector multiplies? Can I reorganize the next level of algorithm and communicate less? And then we're going to get much more significant speedups. So let me go up that next level and talk about what's possible. So we're almost always going to do many sparse matrix vector multiplies, not one. And the class of algorithms that do that include well-known ones like conjugate gradient and GM-res and Lanczos. They're all called Krylov subspace methods. And they all have, and they're both for solving AX equal B and for solving AX equal lambda x. And so what you do is you give them a starting vector, you give them an x1 or an x0, and you're going to do a sequence of k sparse matrix vector multiplies to get a sequence of vectors. So each of these comes from doing one sparse matrix vector multiply. And all of these algorithms have the property that to get their answer, they compute some linear combination of these vectors that gives you the best answer by some metric. And depending on whether it's this algorithm or that algorithm, and depending on whether it's solving linear systems or least squares, is a different definition of best. And people have been inventing these things for a long time. So, but they all depend on getting, a sequence of vectors, taking a linear combination, and picking the best one. And in all of their cases, the main cost is the sparse matrix vector multiplies. And so the question is, can I do anything better now that I know that I'm going to do this sequence where I just keep multiplying the same vector over and over again? So each one of these vectors that I get, I do a sparse matrix vector multiply on the last one. Can I make that go faster? So what would my goal be? My goal would be to have it be as cheap to do k as to do 1, right? That's obviously a lower bound, right? I can't do better than that. So that's going to be my goal. I would like to make the communication cost of doing this, the amount of data moved, independent of k, or as close to that as I can get. That's going to require significant reorganization. So what do I mean? Let me be more specific. So in the parallel case, where I'm sending messages between processors, every time I do one of these guys, I have to send messages, at least to my neighbors. And it turns out I'm going to also do dot products at every step. So a dot product is a reduction. And if I have p processors, that's going to cost me log p messages. And if I do that k times, the total cost is going to be k log p in the traditional algorithm. So k sparse matrix vector multiplies and k dot products, that's going to be k log p messages. I want to do it in log p messages, independent of k. So we have to do some changing the algorithm for that. Now, I will not change the bandwidth costs in the parallel case. When I'm sending messages, I'm only going to change the number of messages. So I can only affect the latency. But in the sequential case, I can do much better. So here, every sparse matrix vector multiply, I potentially have to read the whole sparse matrix from DRAM to cache. Do that k times. That's the most expensive thing in the sequential algorithm, going between memory hierarchies. I want to read the matrix once. I want to read the matrix once from slow memory to fast memory, from DRAM to cache, and take k steps of the algorithm. It's hard to do better than once. Okay. So that's going to be our goal, and to do that, I'm going to have to completely reorganize the way sparse matrix vector multiply is done and actually do a higher level optimization. And I'm going to show you a picture where I can sort of draw all the details. And you'll see, I'm going to make an assumption here. It works well when your matrix can be partitioned with what I'll call a low surface to volume ratio. So I create blocks, and I don't have to talk to my neighbors very much. We've seen that picture before, but let me draw it again. So what I'm going to do now is take the world's simplest sparse matrix tridiagonal and draw in every detail. Okay, so we all know what a tridiagonal matrix looks like. And so what I'm going to do is take X, and it's going to be a 32 by 32 tridiagonal matrix. So I have all the entries of X here represented by dots. All the entries of AX represented by the next 32 dots. A squared X and A cubed X. So I want to compute 3 iterations of A times X. And I'm given the bottom row of X's, and I got to compute the top 3 rows. And so what I'd like to do is ask, how much information do I need to do that? So there's dependencies here. And since my matrix is tridiagonal, what you should imagine is for every dot, it depends on the 3 dots right below it, because that's what a tridiagonal matrix looks like. So A times X, the third entry of AX depends on X sub 2, X sub 3, and X sub 4, because that's what tridiagonal means. And so this picture repeats everywhere, and to make my artwork a little easier, I'll just draw it as a triangle. So the tip of the triangle is what I'm computing, and it depends on everything at the base of the triangle. So this picture repeats everywhere. So for example, if I want to compute that entry of A cubed times X, it depends on those 3 entries of A squared times X, right? So now let me just repeat. What do these 3 entries of A squared times X depend on? Well, they depend on some more entries of A times X. And if I just continue that dependency graph down to the bottom, this entry of A cubed depends on these, however many there are, 7 entries of the original x. So I need all this information to eventually get everybody inside the triangle. Okay? And if I want to compute a whole bunch of entries of a cubed times x, the same idea tells me that I need everybody at the base of this trapezoid. That's what the dependency looks like. Okay, so that's all we need to know to understand what the sequential algorithm looks like. So let's suppose that I want to compute every black dot that you see here, and my cache is so small I can only fit about a quarter of the matrix and about a quarter of the black dots in memory at once. So what can I do? So the first step I'm going to do is I'm going to read in all these entries of x. I'm going to read in all the corresponding rows of my matrix. And that gives me enough information to fill in this blue trapezoid. I know I have enough, given this, to fill in everybody in this row, everybody in that row, and then everybody in that row. And I can't fill in these guys because something is missing, right? I can't fill in this one because I would need that entry of x that's not available. So that is the dependency graph of what I can do if all I know are the first, however many, 8 entries of A, rows of A, and the first 8 entries of x. Okay. So what's the next step? Here's the next step. I'm going to read in the next 8 entries of A and keep a few of the old ones. I'll read in all these entries of x. And what else do I need to fill in this red parallelogram? This guy needs these 2 blue entries, so I better keep that sort of boundary region. This guy needs those 2 blue entries, and this guy needs these 2 blue entries. So I need to keep the last 2 diagonals. So a little bit of extra stuff. And then I have everything I need to fill in the red triangle. So what have I done? I've read in A once, I've read in X once, and I can compute everything and write it out once. And then I do the red triangle, and then I do the green not triangle, parallelogram, and then finally I do the yellow trapezoid at the end. And so in this process, I have read the matrix exactly once, and I have read and written each x exactly once. I can't do it fewer times than that, with a little bit of redundant reading and writing at the boundary, but who cares? Okay, so it's a lower order term. So that's the sequential algorithm. What about the parallel algorithm? So here, imagine again, I'm going to have 4 processors, and I'm going to assign a quarter of the work to each one. So processor 1 will want to compute all of these entries of a cubed, a squared, and a times x. And so the question is, how much information do I need? So what would be the naive algorithm? The naive algorithm would say, well, processor 2, I know this. I want to compute these guys. I have everything I need except that entry and that entry. So I have to have one message from processor 1, one message from processor 3, and then I can compute all those. Once I've done that, assume processor 3 is doing the same work at the same time, I have to have another message with my neighbor and another message with my left and right neighbors to get the next ones. And then one more time I have to have another message to get that entry and that entry. So the number of messages with my neighbors grows depending on how many rows here, what k is. I don't want to do that. I want to have one message with my neighbors. So here's the picture. So processor 2 is going to be responsible for everything in here, but processor 2 is going to do a little bit of redundant work, everything in these triangles. So in one step, what processor 2 is going to do is going to get in one message, it's going to collect these 3 data items are going to be sent from processor 3 to processor 2. And in one message, these 3 entries are going to be sent from processor 1 to processor 2. So now, so it's the same amount of data sent as before, but instead of sending that number, and that number, I'm going to send that, and that. It's the same amount of data, 3 numbers, but it's going to be sent in one message instead of 3 messages. And so with one message at the beginning, processor 2 can now compute everything in that red trapezoid. So let's see what that means. So processor 1 is going to get all these 3 numbers in one fell swoop at the beginning from processor 2 and compute that blue trapezoid. Processor 2, as I said, is going to compute everything in the red one. Processor 3 will compute everything in the green one. Processor 4 will simultaneously compute everything in the yellow one. And so if I draw them all at the same time, I get some overlap there. So the region in this triangle is going to be computed redundantly by processor 1 and processor 2. They're going to compute it, but hopefully if, this is, imagine that that this stretch here is actually a very, very long and skinny parallelogram. So I don't, trapezoid. this is going to be a very small region in practice compared to all the regions that are done just by one. So there's only going to be a little bit of extra work at the end. I mean, we can do the asymptotics. If this is an n by n matrix and I have p processors, the amount of work here is like n over p, and this is, asymptotically smaller than n over p. It's just proportional to k, the amount of work. So as long as n over p is very, very large, why use a parallel machine otherwise? Then the redundant work will be small. So that's the picture for a tridiagonal matrix, which is as simple as it gets. And now I want to say the same idea works for general sparse matrices, except the graph theory gets a little more complicated. So what I've drawn here is a picture of what a general sparse matrix looks like. So there's one vertex for every row or column in the matrix, and there's one edge for every non-zero. So if that's entry 1 and entry 2, there's A12 is non-zero. And these orange dotted lines are my processor boundaries. So processor 1, the guy in the middle, the gray one, he is responsible for all of these rows and columns, and he needs some data from the neighbors. So so let's suppose I only wanted to do A times X, and the gray processor owned all these rows of the matrix and the entries of X. What other entries of X would this guy need? Well, look at the edges to all the neighbors. In order to compute this entry of AX and that entry of AX, follow the edges. It depends on that entry of X. So I need one message from this processor to get that red guy. These two red guys would have to be sent. This red guy, all the red guys, one edge away. Basically, do breadth first search out one from the middle, and that's what's necessary. What do I need to do AX and A squared X? Follow the edges one more level out. One more level of breadth first search. Who are the red neighbors of the red? They're the green guys. So the green guys are 2 away. And if I want to do A cubed, the blue guys. So they're 3 away. So now, this is the same idea as in the last slide. Suppose this guy wants to do AX, A squared X, and A cubed X. What information does he need from his neighbors? He needs things 1 away, 2 away, and 3 away. So this is that little triangle of stuff that I drew in the tridiagonal case. So it's this little triangle here, all the guys at the bottom, those 3 values of X, that corresponds to the red, the green, and the blue. And so in one message, this processor will pack up all the red, green, and blue values of X and send them in one message to the gray. This guy will pack up all the red, green, and blue and send them in one message. Okay. So the question is, so that's the picture, but this assumes that I know how to draw the orange lines. How do I partition among all the processors? Well, we had a whole lecture on that. It's called graph partitioning, right? That's what the graph partitioning problem is, and I want to minimize the number of edge crossings from one processor to the other. That will minimize the communication. That's the parallel algorithm. What about the sequential algorithm? So in the sequential case, let me just go back to the picture. Slow, aren't you? Okay, I just did this from left to right. So if I have a general sparse matrix, there is no obvious left to right or top to bottom of the matrix anymore. So let me go back to this picture here. So what this says is I have to put some order on all of these regions. Here's a region owned by this processor, by that processor, by that processor. In what sequential order do I process them all? Well, that's an optimization problem, right? If I did this one first and then that one, would that be a good idea? Do they share any data? If when I'm finished to this guy, would he leave any useful data in cache behind for this next one to use? No. I should do a neighbor, right? So the question is, which neighbor? Well, that turns into the traveling salesman problem. If you write down a graph which says, for each of these blocks that I would work in cache, how much useful information would it leave behind if I did that block next, or if I did that block next, or if I did that block next? So for each of these blocks, I would have an edge to a neighbor which says, how useful am I to you? And then what you want to do is traverse these in some order where you maximize the total usage. How much data, useful data, you leave behind. And that can be formulated as a traveling salesman problem. And so that's a good optimization too. So the question is, does it pay off? And so here are some speedups to show you how much it pays off on a whole bunch of different sparse matrices. From many different walks of life. This is the simplest case. This is a 5-dimensional matrix. So it's not tridiagonal, it's pentadiagonal. And there's a 9-point stencil. There's optimizations of gearboxes and circuits for the xenon and so forth. So, and all of these are publicly available. So the red bar is how fast you can do SPMV. The vertical axis is gigaflops, so up is good. And the green bar is how much faster it went if you did the optimization I just told you about. And so the best case, which is just barely wider than tri-diagonal, is 6.4 times faster. And it also indicates what's the right value of k. Because k is now a tuning parameter. How many steps do I take at once to do this? And there the answer was 50. So that was how many. So in other words, in this picture back here I went from a to a squared to a cubed. Why did I stop at 3? It was so I could draw the picture. But I could go an arbitrary distance. And the question is, how far is it worth going for a particular matrix? Because the farther I go, the more redundant work I do. At some point, it's not worth going any farther. So this number up here, this k, which is 3, that's a tuning parameter. And so this picture shows you the result of tuning. K equals 50, that was the optimum. We did search over all the tuning parameters. K equals 14, K equals 4, K equals 3, some K equals 15, right? So depending on the sparsity structure, it was more or less worth doing this optimization. Okay, and let me add that, so let me do a little bit more summary of performance numbers. So the best speed up we saw in that case was 6.4. There was also some work done where the slow memory was disk and the fast memory was DRAM. That's another case where communication is expensive. So that's out of core speed up. And there was a speed up of up to 3x. There was a model of running this on a petascale machine. There was up to a 6.9x. And then there was a running on the grid, a bunch of processors in different cities, very low bandwidth and high latency. There was a speed up predicted of up to 22x. So depending on your architecture, you can get more or less good speed ups. So let me just repeat that the sequential speed ups, when we ran this in the sequential case, the speed up was due to the bandwidth. The amount of data moved between slow and fast memory went down by a factor of k. That's always a good idea. In the parallel speed up, it was due to minimizing the number of messages. So it was only reducing latency. The math is that you can't send less information because you need that information to compute the answer. So it has to be there. So you can't send less data. You can only send it in bigger lumps and have fewer messages. And these speed ups here that I'm showing you use both techniques. This was multi-core. So there were two kinds of communications we wanted to minimize. One was moving data from off-chip to on-chip. That was the sequential optimization. And the other one was moving data in between cores on the chip. So that was the parallel optimization. So those two pictures I showed you before were both used. It was a hybrid of both optimization schemes. Okay. So that tells us that it's well worth computing not just AX, but a whole bunch of matrix vector multiplies at the same time. But is that useful for anything, right? Because the original algorithms that motivated us to think about that, conjugate gradient, GMRes, they don't use that. They multiply. They do a lot of matrix vector multiplies, but they do it by different vectors. So they don't take AX, A squared, X, A cubed, X the way I did it. They take X, and then they compute AX, and they take a linear combination of X and AX, and then they multiply that by A. So it's a totally different set of vectors that they multiply by. So now we have to think one level yet higher in the stack and ask ourselves, how do I reorganize the solver, which was my goal in the first place, to use this new kernel that I just invented? So let me just give you a picture of the simplest such example, which is called GMRes. But it's typical. So all of these solvers, either for AX equal B or AX equal lambda X, they're going to do K sparse matrix vector multiplies. They're going to get a whole bunch of vectors out. And then, based on some mathematical definition, they're going to find the best solution, the best linear combination of all those vectors to minimize the error by some metric. And there are a lot of ways you can do that, so there are a lot of algorithms. Conjugate gradient, GMRes, and so forth. And so what we need to do is ask, can I reorganize the math of those algorithms so I can still compute the same linear combination, but starting from different vectors? So I want to get the same answer, but it's going to be a linear combination of different vectors. Because it's not going to be, these guys, the original algorithms don't take linear combinations of X, A squared X, A cubed X. It's different vectors. Okay, so I will show you what that looks like. And the goal is going to be the same. I want all the benefits that I just showed you for this kernel to accrue to the higher level algorithm. So in the parallel case, I want the number of messages to become independent of how many steps I take, to go from k log p to log p. And in the sequential case, same thing. I want the amount of data moved between slow and fast memory also to go down from k times, to take k steps, down to 1 time. And so people have been thinking about these algorithms for quite a while, but we really didn't sort of figure it out well until Mark Homan's PhD thesis in 2010. And he did many algorithms in that thesis, and you can read on it in the Bebop webpage. I'm just going to show you one algorithm. And so here it is, and it fits just in a few lines of code at this level of detail. So it's called generalized minimum residual, and I want to solve AX equal B. So it's going to form a basis for this linear space. It's not going to compute A, B, A squared, B, A cubed, B, but it's going to be a bunch of vectors that still live in this subspace, and it's going to compute some vector to minimize the 2 norm of the error. Okay, so let me tell you what the standard algorithm does and how much it costs, and then I'll do the new algorithm. So here's the standard algorithm. I'm going to take k steps. I'm going to do a matrix vector multiply, get a new vector, and then I'm going to run an algorithm called modified Gram-Schmidt. I'm going to take this vector and make it orthogonal to all the ones I computed before. And how does Gram-Schmidt work? Well, I got to take a dot product, and then I got to subtract a multiple of v0 times w to make w orthogonal to v0. Then I'll do the same thing with v1, take a dot product. And so anyway, a lot of dot products, a lot of Saxbys. And then I get a new vector, vi. And that's the one I multiply next. So I'm going to do a whole bunch of matrix vector multiplies, but I do all this other stuff in between. So this is not a squared, a cubed. And then when I'm done, there's a little least squares problem of size k by k that I solve to get my answer. So it's little stuff. It all fits in cache. Don't have to worry. So how much does this cost? Let me just tell you, there's a sequential version and the parallel version. The sequential version, well, here's the loop. I'm going to do something k times. I'm going to do k sparse matrix vector multiplies. How much is that going to cost me? Well, if I have NNZ, number of non-zeros, if that's how big my sparse matrix is, I'm going to move that matrix from DRAM to cache k times, so k times NNZ words moved for the sparse matrix vector multiplies. And what about all these dot products and Saxbys? Turns out there's k squared dot products and Saxbys of vectors of length n, so k squared n. That's the cost of modified Gram-Schmidt. In the sequential case, each sparse matrix vector multiply, I got to talk to my neighbors, so order k messages. And for all of these dot products in modified Gram-Schmidt, there's k squared dot products, so there's k squared log p messages. So that's the standard algorithm. Here's the new one. It's 3 lines of code at the right level of abstraction. So I'm going to start by doing that kernel I just told you about, v, a squared, v, etc. That gives me a whole bunch of vectors. I'll put them together in a matrix W. Now, these vectors are not orthogonal to one another. What this modified Gram-Schmidt did was it tried to make them orthogonal. So I can't use, these don't match the original algorithm. So I have a whole bunch of vectors. I want to make them orthogonal. That is a problem I talked about in dense linear algebra. It's called the QR decomposition. And we have a communication optimal version of that. And so using a result from a lecture last week, I will call the new optimized tall skinny QR, take all of these vectors, of which there are k plus 1 of them, and reduce it to orthogonal times upper triangular. And these vectors are the same as the v's I would have gotten from there. But I've done the math differently because I had to. And the rest of the algorithm stays the same. So now what's the cost? Well, I only had to read the matrix A from slow memory to fast memory once in the sequential case. So the cost went from k steps times number of non-zeros to the number of non-zeros. The number of words moved from modified Gram-Schmidt dropped also by a factor of k. So the cost dropped by a factor of k in the sequential case. And what about the parallel case? I only have to do, order 1 message to do this. I showed you that before. And then how about my tall skinny QR in parallel? Recalling my lecture from last week, I can do that in log p messages. So 1 reduction operation, not k squared reduction operations. So you can see that the costs have gone down significantly. And so everything I've told you is, sounds great. It's completely true in exact arithmetic. But we live in the real world, so there's a big bug with this program. If you actually ran it, which I will on the next slide, you'll get garbage. So does anybody who hasn't heard this before have an idea why you get complete garbage? So what have I not taken into account. So what are all these vectors that I'm computing a squared, a cubed times v? Do you know what happens to that, to these vectors as I keep making k larger and larger? Here,
It's become numerically unstable.
And the reason it becomes numerically unstable is all the vectors in this basis here are becoming more and more nearly parallel to one another. They're all becoming nearly parallel to the eigenvector of A for the largest eigenvalue. So everybody in the world depends on this algorithm who uses Google. Do you know why? This is how PageRank worked originally. So you wrote down a matrix, which was, one row and one column for every web page, and it said which web page was pointing to which other ones. And the way PageRank worked is it wanted to compute the eigenvector for the largest eigenvalue of that matrix, which said which web page was connected to which other one, and this is the algorithm they used. Okay, so the point is, all of these vectors are becoming nearly parallel to one another, and are nearly parallel vectors a good basis for a space? If they're all pointing in the same direction, they don't tell you very much information about a whole high-dimensional space. So let me just show you a picture about what the convergence looks like. So I'll run that algorithm, and I'll compare it to the usual algorithm, and we'll see what happens. And so the horizontal axis is the number of iterations. The vertical axis is the log of the error, so down is good. The black line is the classical algorithm, which is converging nicely. And the blue dots are the algorithm I just told you about. So in exact arithmetic, everything is perfect, except in real-life floating-point arithmetic, it's complete garbage. And so that's because this basis, and I'm going to call it the monomial basis, just to give it a name. So it's totally numerically unstable. So why am I calling this the monomial basis? Well, these are polynomials in A, aren't they? A squared, a cubed, those are polynomials. And they're the simplest possible polynomials. They're called monomials. Now, there are a lot of polynomials in the world that one could imagine picking. Let me pick a better set of polynomials. And I get the green triangles. And it works perfectly well. So what I have to do is do the right numerical analysis to realize that there are certain polynomials that will keep these vectors nice and numerically independent, and they'll give me a great basis that spans the space, and it'll work fine. And so I have to make that optimization as well, in addition to the computer science optimizations. So, question?
How did you pick your vectors in the first place?
So the original vector, so the question is, how did I pick the vectors in the first place? So the original one is the right-hand side. So I want to solve ax equal b, so the very, very first vector I start with is b. It's the only vector I know to use. And then everything else is generated starting from that original vector b.
And so that's why it becomes more parallel in this case.
So no matter which vector I started with, it could be, and it's a theorem, I could pick a random b, and all of these vectors will, with probability 1, converge to the same direction, which is the eigenvector for the largest eigenvalue. Yeah, it's called the power method in linear algebra, yes. And Nick has a question or a comment.
Starting with B in this way, maybe there's different notations for GMRes, but basically this is the same thing as starting with the initial guess x equals 0. So that's a safe assumption that x equals 0 is not an eigenvector.
Right. Okay, so what are the final speedups when we put it all together? So this is running that GMRes algorithm on an 8-core Intel Cloverton, and it's on a whole bunch of different sparse matrices, and it's optimizing everything. So I had to optimize the kernel that computed ax, a squared x, a cubed x. Of course, it's computing a different polynomial, so I had to pick a good polynomial. And what I'm showing here is the speed, or the time, the speed normalized to one of the classical algorithm. So the original GMRes, none of these fancy optimizations, but for the best possible matrix vector multiply you can use. And then this higher bar is how many times faster the new algorithm goes. So it goes 2 times faster, 4 times faster, whatever. And it's broken down into parts to tell you where all the time is going. So we know which is more important. Is it the sparse linear algebra part or is it the dense linear algebra part? Because there were two kernels here. This is the sparse linear algebra part, and this QR decomposition, that's the dense linear algebra part, and they're both important, and depending on the sparse matrix, either one might be the bottleneck. So that's what I'm trying to show here. And so the red part is, let me make sure I'm saying this right. So the red part is the time spent in the matrix powers kernel, the new optimized kernel, and the blue part is the unoptimized one. That, so this is relative runtime, so I think I may have told you the reverse. So this is all normalized. The new algorithm runs in time 1, and this is how many times slower the old algorithm runs. So the speed up is still here, 2, 2, 4, and so forth. But it's all normalized to be the new algorithm runs in time 1, and the old algorithm runs in time of the higher bar. So now let me more carefully say what this is. So the red is the new sparse algorithm, and the blue is the old sparse algorithm. So the blue time shrinks down to the red time. And for some problems, that's enormous, and for some ones, it isn't very big change at all. Now, that's the sparse linear algebra. Now let's look at the dense linear algebra. All of the modified Gram-Schmidt, the dot products and the Saxbys, that's purple, and that shrinks down to the yellow and the orange. So here, all the time is spent doing the dense stuff, and here, for everybody else, it's more balanced, about half dense and half sparse. So both had to be sped up appropriately. You know, if I'd only sped up one, I wouldn't have gotten a good speed up. Now, when we first did this optimization, we did it in the natural way. There was one student who was working very hard to make the sparse linear algebra kernel go as fast as possible, and somebody else was working on the dense linear algebra. They independently optimized them, made them run very fast, and we put it together. So the inner loop of the program did just this. It called one student's sparse matrix vector multiply and the other student's dense linear algebra. And the result was terrible. It slowed down dramatically. And the reason was that the two kernels were fighting over the cache. They each assumed that they owned the entire machine, and they were optimized to use all of it optimally, and so they spent all of their time copying things back and forth in between the two kernel calls in the inner loop. And it slowed down dramatically compared to the unoptimized code. So then they went back to the drawing board and did what's called co-tuning. They tuned them, realizing they had to share all the machine resources, and then the speedups occurred. And so what this means is that tuning is no longer library by library or subroutine by subroutine. You have to tune the entire application to make sure the resources are appropriately shared. That complicates life, but it makes for interesting research opportunities. Now, you don't have to take my word that this is a good idea. You can take the word of somebody at a higher pay scale, like President Obama. And so there was a quote in the 2012 Department of Energy budget request where they had which is a huge document, but there are a few pages of highlights from each year. And in this one, it says that avoiding communication is a good idea, and this new algorithm is going into this new library called Trilinos. So, after seeing this, we went and talked to the author of Trilinos, and he was indeed referring to the algorithm that we're talking about. And indeed, Mark Homan, who is a graduate student here, is the postdoc working on this project, incorporating the work, these algorithms into the Trilinos package, which is one of the main solvers in the Department of Energy. Okay, so it's referring to that particular work. So so this is just one example. There's actually a very large set of other related opportunities to tune that haven't been done yet. So let me just sort of give you now a high-level overview of what the tuning space looks like. Because there are a lot of ways that sparse matrices are represented, and the way I've talked about tuning them has to be changed slightly for each way. So when you store a sparse matrix, what do we actually have in the matrix? There's non-zero entries, and there are the locations. And either one of those can either be explicit or implicit. Now, what we've been talking about so far is where everything is explicit. It's called CSR format. So I have an explicit list of all the non-zeros. So that costs me order NNZ memory, number of non-zeros. And I have all the indices. That costs me another big O of number of non-zeros. And we've just been talking at great length about how to optimize that. But there are an awful lot of other sparse, let me call them linear operators that come up in practice that people want to optimize. So for example, vision is one of the big applications in the Parlab. And in that case, you have one non-zero for every pixel. You have, one row and column in your matrix for every pixel in your image. And I think I've said this before, the matrix entry says how likely these two pixels are to be part of the same part of your image. So you have to store all of those non-zeros explicitly, but you don't have to store any indices. You know what an image looks like. You know, it's this two-dimensional array of pixels. You know where all the pixels are. You don't have to store the indices at all. So that's a very large, so there's little o of NNZ storage for that. You only have to optimize this, and then there's some special code that understands where they live, that understands the indices. That's explicitly coded. So, and so this can also, all these optimizations I'm talking about need to be changed to take into account that the non-zeros are explicit, but their locations are implicitly given by the fact that it's an image recognition problem. So we talked about the graph Laplacian. That comes up in graph partitioning. And in that case, the indices are given to you explicitly. It's an arbitrary graph. But you don't have to store the values, because you know they're negative ones in the off diagonal and the degrees down the diagonal. So you certainly don't have to store the values. And then there's another example, which we'll talk about actually because it's part of the structured dwarf, the structured grid dwarf. It's part of a different dwarf. They're called stencils. And think tridiagonal matrices, where you have constants along the diagonals. So a stencil says, I have a one-dimensional array, and I'm going to compute the average of my neighbors at each point in the array. And it's going to be the same weighted average at every point. In that case, I know exactly what each matrix entry is. It's maybe 1 half, 1 half, 1 half. I don't have to store all those 1/2s because I know it's the same everywhere. And if it's just a tridiagonal, I certainly don't have to store the subscripts of where they live. And those come up all the time, for example, in Laplacians, 2D Laplacians. So that's yet a different optimization space. And so in addition to that, there's different operations. I talked about a squared, a cubed. They're different polynomials. These you optimize in pretty much the same way. Depending on how many columns of x you have, you can take advantage of having more columns of x to get more data reuse. That's worth doing. Some of these algorithms require not just a times x, but a transpose times something else. So you might as well compute, if once you have a in memory, you might as well compute a transpose times y at the same time and double your reuse. And some algorithms require all of these vectors, and some only require the last one. So there's a great big design space of things that people want here. And, and it would be tedious to do it all by hand, which is the way it's being done now. So the open research question is how to automate it. And that brings me to my very last slide, which is possible class projects. You can come to Bebop meetings on a weekly basis and hear about many more of them, of course. But you could experiment with sparse matrix vector multiply in different architectures and ask which of these many optimizations are the best. You can try taking this Pyaskey package, which we're about to release, and just use it, try it on different applications, different architectures, which ones work best. You can try to add your own optimizations to it if you like. If you have a particular application you want, you can apply these optimizations to your particular problem. It can come from data mining, bottom solvers, and adaptive mesh refinement, and see which optimizations work best for your particular matrix. And then you can explore this tuning space, right? I told you about one particular way of doing it, but there's a lot of different matrix representations. That's what the last slide was about. And there's a lot of other Krylov subspace methods that I didn't mention. GMRes is the tip of the iceberg. There are quite a few others as well. And there are people who are working on actually using compiler technology to automate this process of optimization. This is called the sparse polyhedral framework. It's one of many different compiler tools that people are building. And if you're interested in that, more details are available. So that's the end of today's lecture, on time for a change. Next time, we're going to have 2 lectures. A short lecture on a new tool that we'd like you to try using to automatically find race conditions in parallel code. Because we've decided to give you a buggy version of the next assignment. It will have a deliberately inserted race condition. We know where it is, of course. And a tool that will find it for you automatically. So what we'd like to do is have you use this tool, which is installed on Hopper or is being installed, and make sure that you know how to find race conditions automatically. And we'll also start talking about the n-body problem. So that's the end of the sparse dwarf.